currently working as a postdoctoral research associate at Sydney's Sussex College and the Kavli Institute for Cosmology at the University of Cambridge under Professor Roberto Maiolino and Dr. Sandra Tequera. He is a member of the Galaxy... ¿No se me oye? Ups. Okay.
Que sí que se le oye.
Sí le oímos, sí.
Sí que se oye.
Ah,
A mí que
justo.
sí que te oímos.
Vale. Yo soy vosotros. Sorry for the mishap. Joris is, well, he's a member of the Galaxy Formation and Evolution Group and primarily focuses on observational data of high redshift star-forming galaxies from several major observatories. Joris is also actively involved in various projects with multiple collaborators. Particularly noteworthy is his participation in the James Webb Space Telescope Guaranteed Time Observations, the collaboration of its NIRSpec instrument, as well as his role as an associate member of JWST, the JWST Advanced Deep Extragalactic Survey. Additionally, he collaborates with the Atacama Large Millimeter Submillimeter Array, ALMA, the Hubble Space Telescope, and the Very Large Telescope facilities. Dr. Joris is also involved in large-scale cosmological hydrodynamical simulations aimed at accurately modeling the intergalactic medium. Today, Joris will discuss the origin of metals and dust within galaxies in the first billion years of cosmic time. Thank you very much, Joris. The floor is yours.
All right, thank you very much for that introduction. And yeah, let me first of all say I'm very happy to be here. So thank you for inviting me to present some of our work. Let me just check again. You can see my slides all right and hear me fine before I get started.
It's fine.
Yeah, all good.
Yeah,
okay.
we can.
Excellent. So yeah, as you just mentioned, I'll be talking today about the origin of metals and dust within the very first galaxy. So galaxies roughly in the first billion years of cosmic time. And of course, a lot of this work that I'll be presenting was done in collaboration. And mainly that is I'll be trying to showcase some of the latest findings from JWST and also the JADES program that I'm heavily involved in. So without further ado, let's get started. So just first, we'd like to sort of zoom out and really look at the big picture here. So what you're seeing is, I'm sure a picture some of you have already seen before, namely a rough timeline of galaxy evolution. So it all starts on the left with the Big Bang, of course, and then we have the recombination epoch. So when the CMB radiation was released, and if we then go to the present day on the other side, we see sort of almost the polar opposite image. So in the beginning, the universe was very uniform. You had very, very marginal density fluctuations. And today the picture is completely different, and the universe shows enormous complexity. We see all this structure, all various types of galaxies, and really the goal of galaxy formation and evolution as a whole is to try to explain this whole picture. And of course, we're going to then focus on what happens in between and how we get from these tiny density fluctuations to the formation of the first objects in the universe, which then led to the reionization of the universe, and also then further on led to all the galaxies that we see around us today. And you'll notice here that there's actually two scales. So very rough indication. We have redshift on the bottom, which I'll mainly be using here, and you can see this is highly non-linear. So the present day, we're at redshift 0, so redshift plus 1 is 1, and then the reionization epoch is sort of at redshift 10-ish, and we start all the way at redshift of 1,000 when the CMB was released. Right, so let's zoom in a little bit then on this first epoch. So going from these, as I mentioned, the density fluctuations that we see imprinted on the CMB, and how these density fluctuations actually connect to what really the first objects we can observe in the universe, which are, the very first stars and galaxies out maybe at redshifts, we're not entirely sure, but redshifts sort of 20 to 30 potentially. And so the dark ages here, they look very boring. There's not much going on in this picture, but really this is quite an important epoch if you look at galaxy formation, because within the lambda CDM cosmological model, this is actually where dark matter starts to collapse, and we get the growth of these dark matter halos that then make sure that gas is able to fall into them later and cool down and form these first objects. Okay, so then when we start to form the first stars, these very quickly start to emit a lot of ionizing photons because they don't have any metals to cool them, and I'll come back to this more later on. But because they don't have any heavy elements, that means they're, on the whole, quite massive, very likely, and they're very efficient at producing photons that have high enough energy to ionize helium and also hydrogen. But what also happens with the formation of these first stars is that very quickly after the first stars form, which we refer to as the population 3 stars, they will explode in supernova events, and these will spread metals throughout the universe. And they do this really quite quickly. So it only takes a few million years after the formation of such a very heavy star for it to reach at the end of its life and then explode as a supernova. And it turns out this metal enrichment is actually very efficient. So that means that finding these pure population 3 stars, so stars without any metals, is actually quite a hard task, because very quickly you start to get metals throughout the universe, and the following generations of stars, so the population 2 stars, will then form with already some heavy elements in them. So it's not pure helium hydrogen stars. Okay. Then if we go a bit further and we start to look at the reionization epoch, this is quite a remarkable phase transition, because it only takes a few 100 million years, really, from the formation of the first objects until we get to the point where the whole universe is reionized. And why this is not so simple, we'll get to into a little bit more. But basically, the universe is very big, and there's a lot of hydrogen that needs to be reionized. And so what this means is that actually the first stars and galaxies seem to be quite efficient at producing these ionizing photons, as I mentioned. And also somehow there's some mechanisms that allow the photons to reach the intergalactic medium. So to go into that a bit more, the way we usually think about cosmic reionization is in terms of these, we sort of break it down into 3 factors. And this is all from a viewpoint of a framework where galaxies are responsible for reionizing the universe. So we start out with the UV luminosity density, that's rho UV here. And this is basically just, you can observationally determine this just by counting the number of galaxies. So we construct what's called a UV luminosity function, which just tells you the density of galaxies with a certain UV luminosity. Then we need to translate the UV luminosity, which is just measured around 1500 angstroms. So that's ionizing photons. But then this Xi ion is what's called the ionizing photon production efficiency, which converts the UV luminosity to the actual number of ionizing photons. And then finally, there's this escape fraction, F-esque, and this tells you how many photons are actually making it out of the galaxies into the intergalactic medium. So in a very rough sketch, you can imagine something like this, where you have a population of stars within a galaxy which are producing these Lyman continuum photons, but some of the very dense neutral gas within the galaxy might actually stop them from escaping. And so it's only a few of them that actually make it out and reach the neutral intergalactic medium. And actually, if you, it turns out if you look at local galaxies, so within our neighborhood, we actually barely see them leaking any ionizing photons. So this means, as I mentioned, that actually these galaxies need to be quite efficient. And just to mention that, to sort of complete the whole picture, we also need to then take into account the actual recombinations that happen in the intergalactic medium. And usually the way we do this is by turning to cosmological simulations, where you can keep track of the density and temperature of all the gas, and that then tells you how many of the hydrogen atoms in the intergalactic medium will recombine and become neutral again. And so, as I said, the production and escape of Lyman continuum, so ionizing hydrogen ionizing photons, actually turns out to be quite efficient. So you need escape fractions, just to give you a rough number, of about 10 to 20%. Whereas, as I mentioned, in the local universe, this is very rarely seen. And so this is already telling us that, you know, these first galaxies are quite different in many ways. Okay, so then if we think about the metal and dust content, which is actually highly coupled with this process of reionization, as I've been trying to sort of sketch out, because, as I mentioned, this early on, at the point where we have the first stars and galaxies forming, this marks the point, of course, where the first metals are being produced, because those very first stars will start to make the first heavy elements. And then, of course, a lot later, so I've indicated here the formation of the solar system. We know that at this point, a lot of metals have been created. And so along the way, that means many generations of stars will have created more and more heavy elements that have all built up and today make up, you know, our solar system. So really the question is, you know, what happens at this very early reionization epoch, and what do these galaxies, how quickly do they build up their metals and dust? And this is really important to know, because if we know these first stages, then we can start to evolve this picture and really try to, you know, connect the two ends, where we know the very first stars will be completely lacking of metals, and at the other end we have, you know, the solar system as we know it, with all the carbon, oxygen, iron, and so on. So if we go to a review here by Daniel Stark, this is on our view basically of galaxies in the first billion years, as we know it from HST, the Hubble Space Telescope. So if we look what it says here, it says the galaxies tend to show blue UV continuum slopes, low stellar masses, very minimal dust obscuration, and evidence for metal poor ionized gas. So basically, all of the hints, all of the observations, the way we interpreted them from HST, so this was in 2016, we basically thought that all of these galaxies will be basically free from dust and probably have, a very small amount of metals. And now in the rest of the talk, I'm going to go over how this picture has evolved. So what we've learned from ALMA in the far infrared, but also from, of course, JWST and over the last year, which has been showing us some very interesting, I think, new results on what these galaxies actually look like. And just to sketch out how we actually go about doing this. So observationally, if we want to look at the rest frame optical from the ground, you're limited really to redshift 3.5 and below, just because of the atmospheric transmission. So rest frame optical lines are very useful to measure things like the metallicity of a galaxy or the dust obscuration. But previously, so before JWST, we could really only do this up to redshifts of about 3.5. And then if you go to the rest frame UV, you can, there's a few lines which are much weaker though than in the optical, but even the brightest line, Lyman alpha, that will start to be absorbed by the neutral intergalactic medium around redshift 7, more or less. And even before JWST, ALMA was already starting to change this whole picture with our access to some of the far infrared emission lines, and those I won't have time to touch on today too much. But at the same time, ALMA also gives us the opportunity to look at the dust continuum emission of these galaxies, and so that makes it a very powerful instrument in addition to JWST. So just to show this in a little bit more detail, we have here, as a function of redshift, the observed wavelength of a lot of emission lines. And so ground-based instruments can't really observe past a wavelength of about 2 microns. And you can see that all these lines, the rest frame UV lines, are basically then the only lines you can see out in this high redshift regime. Whereas with JWST, actually now we can access all these rest frame optical lines, which are, as I said, powerful tracers of the metallicity of galaxies, out to redshifts even up to more or less redshift 9, 10, which is really just revolutionary for high redshift studies. And now we, as I said, have lots of data coming in from the first year of observations, first year and a half almost already. But next to that, as I said, ALMA then has this full far infrared wavelength regime. So these are now millimeter wavelengths, where there's all these far infrared transitions and also the dust continuum that we can see. And so this is really important because it really gives us this alternative view of these galaxies in wavelengths that we can't really study with any other instruments. And just to illustrate what we can do with JWST, so I'm part of this collaboration which is called the JWST Advanced Deep Extragalactic Survey, or JADES. And this is an effort by both the NIRCam and NIRSpec instrument teams. So NIRSpec is the spectrograph and NIRCam is the near-infrared camera. And what we do is we take observations in parallel. So while NIRCam is taking images, just showing a nice inset here from one of our one of our deep extragalactic fields. We're at the same time with NIRSpec placing all these tiny micro shutters over lots of different galaxies, focusing mainly on high redshift galaxies, and taking their spectra with NIRSpec. And so this is a really powerful combination where we both get very deep imaging, and then we can use that imaging at the same time to select these galaxies and follow them up with spectroscopy. And we do this in the GOODS fields, so GOODS North and GOODS South, which also contains the Hubble Ultra Deep Field. And just to give you some numbers, some of our deepest spectra so far will reach about 10 to 30 hours of exposure on single sources. And so the sensitivity we reach in spectroscopy is about 27 to 29 AB magnitudes at 2 micron. And so both in terms of the wavelengths that we're covering, but also just the sensitivity, this is orders of magnitude improvement over what was possible before. And to just highlight very quickly a few first results. First, I thought I'd show what really was the state of the art in the field. So this is a paper from 2017, a redshift 8 galaxy where from the ground you can take a spectrum in the near infrared, and you can see just from this data how noisy this is. So from the ground you have all this all these skylines interfering with your data, and it's very, very difficult to actually properly measure things. But so here, if you can squeeze your eyes a little bit, you're just about able to make out 2 detections of emission lines, which are the carbon-3 rest frame UV lines in this galaxy. And so this was really the best we were able to do, maybe for a handful of objects before JWST. And just to put that in perspective, this is a spectrum of a redshift 10 galaxy, 10.6, quite famous GNZ11 object, which now you can see all of these wiggles are not noise. These are actually individual emission lines, and we can detect very nicely the continuum emission as well, all the way from 1 to about 5 microns, all in one go, with incredible signal to noise. And so this is just completely blowing out of the water what we were able to do before, and we can now start to really dig into what are the physics of these very high redshift galaxies. And this turns out to be a very interesting object. We see Lyman alpha emission, which is very unexpected at such a high redshift. There's even evidence for an active galactic nucleus, and also potentially nearby, not in the galaxy, but nearby, there might be indications for a POP3 stellar populations. So really metal poor or lacking metal stars. A few other results here. So you might have seen that some of the most distant galaxies that have been spectroscopically confirmed, we've been able to do this with our NIRSpec measurements. So up to about a redshift of 13, which is only a few 100 million years after the Big Bang, we can now establish with NIRSpec confidently that these are actually high redshift galaxies. These are not interlopers, but they're actually at these redshifts. And what is kind of interesting is that we barely see any emission lines here, and that I'll get into a little bit more later. But this is not completely due to the signal to noise we have here, but it might actually be just the signature that these are such early galaxies that they don't really contain any metals to for us to see any emission lines. And on this specific object, actually a redshift 11 object, we have some very deep ALMA observations coming up, which can also simultaneously probe the Dutch continuum. So that should be really interesting to see what that produces. And yeah, hopefully we'll know more soon. So what are some of the results on the metal content of these very first galaxies? Well, this was a study by Mirko Kurti on the JADES data. And what you're seeing here is what we call the mass metallicity relation. And so what this is plotting is a measure of the metallicity, which we measure through the oxygen abundance. And then on the axis, we have the stellar mass of these galaxies. And first of all, if you look at the black line here and the contours, this is from the Sloan Digital Sky Survey. So these are basically redshift 0, very local galaxies, and they form this quite tight sequence where with increasing stellar mass, the metallicity also goes up. And this you can understand from the fact that if a galaxy starts to accumulate stellar mass, start to form stars, these stars will also produce metals, and so the metallicity of the galaxy also goes up. Then the orange and red lines, these show the relationships at redshift 2 or 3. So you can already see that as you go to the more distant universe, these galaxies at the same stellar mass become slightly less metal rich. And now the blue and yellow lines here show what we can measure for some of the highest redshift regimes with the JADES data. And so you can see, first of all these galaxies are much lower mass, so they have a lot less stars in them. But secondly, their metallicity is also a lot lower. And so this is showing us that there is still this relationship between the stellar mass and metals, but it seems that both the normalization and potentially also the slope of this relation is starting to change as you go to earlier and earlier times. And we can also appreciate just from the error bars here and the uncertainty still is that actually there's quite a lot of scatter in this relation. So there's some galaxies that are more metal rich and some that are a little bit less metal rich. And this brings me to just one, I think, very surprising case I want to highlight, which sort of seems in contrast to what I've just told you, which is that this pair of galaxies at a redshift of almost 7, so this is only 800 million years after the Big Bang, seems to be very heavily obscured by dust and also very metal rich. So the visual extinction is about between 1 to 3 magnitudes, which we can confirm with NIRSpec measurements. And it also has a very extreme stellar mass, and as I mentioned, the metallicity is extremely high for this early on. So it has about 50% solar metallicity, which is quite significantly in tension with this mass metallicity relation for the majority of galaxies we see. And this is not the only example. There have been other cases also seen with ALMA of what seems to be very extreme galaxies that are very metal rich already very early on. So that kind of brings me back to the question, what do we actually know about how quickly metals and dust build up early in the universe? And I want to focus a little bit more on the dust specifically here. So dust is a very key player in all of galaxy formation, really, because dust grains within galaxies can actually help star formation quite a lot. So they can catalyze molecule formation and also gas fragmentation. So it helps the gas cool down and collapse into what will be new stars. At the same time, though, these dust grains absorb quite efficiently UV and optical light, and after absorbing this light, it will re-emit thermal radiation, which we then can see in the infrared wavelengths as well. So in this galaxy, just as an example, you can see all these dark strokes here. These are actually lanes of dust that are just obscuring the blue young stars that you can see, past these dust lanes. And so, as an observer, that actually makes dust, quite annoying because it takes away our view of some of these stars, and it therefore is an important factor even to take into account when you're trying to measure how many stars a galaxy is forming, if you're just basing your measurement on UV and optical wavelengths. And just to show very schematically what this looks like, so this is a spectrum, a typical spectrum of a galaxy across all wavelengths, really. So it goes here from the rest frame UV to the rest frame optical with some of the main rest frame optical lines. So these are H alpha and H beta, some of the Balmer lines, and then into the mid infrared wavelengths, and finally the far infrared. And this kind of shows you why JWST and ALMA can be such a powerful combination to really fully understand how dust impacts our view of galaxy formation. So at the rest frame UV wavelengths, you can see in this inset, just if you change the amount of dust obscuration you have, this will most dramatically impact you at the shortest wavelengths, because dust will be most efficient at absorbing it there. So you just, the effect of adding more dust here is that the slope of the continuum will change quite drastically. And you can also measure this, for example, from these emission lines, which in the absence of dust always have a fixed ratio, but then if the dust is starting to obscure the H beta line slightly more than the H alpha line, you can measure how much dust is present. But as I mentioned, the absorbed energy is then emitted, and so depending on the kind of dust grains, you either emit them at mid-infrared wavelengths, where you have very stochastic heating. So these are very small grains that are heated to a few hundred Kelvin and then emit at mid-infrared wavelengths, or the slightly larger grains, which are slightly colder, sort of the region of maybe 10 to 100 Kelvin, which then emit as pretty much as a black body. So we see this as this big bump in the far infrared. And to focus on this is actually what we can then observe with ALMA. So these colored bands are showing some of the ALMA observing frequencies. And as I mentioned, this is what we call the cold dust component. So this is the larger grains that are slightly colder, whereas this is emission by, for example, pH molecules. And this far infrared SED, so the cold dust component, is actually relatively simple to model. So relatively simple because we also usually don't have that many data points. So this is an example of a redshift 7 galaxy where we have just a few data points. And basically what we do is just fit this, what's called a modified black body. So this just takes into account that the underlying dust distribution, or the dust grains, will have a distribution of temperatures. And this is just an example of one of the fits you can do, and the kind of parameters you can constrain, which are the temperature of the dust, most importantly. So with this temperature, you can then characterize, how cold the dust in a certain galaxy is, and at the same time, you can also make some estimate of how much dust mass there is in a galaxy. So what have we learned in the past few years then? Well, ALMA's actually detected some very large reservoirs of dust, up to masses of about 10 to the 8, all the way out to redshift 8, when the universe was only a few 100 million years old. And this is just one example of a redshift 8 dust continuum detection with ALMA. And what we've actually also seen, what might be a little bit surprising, is that the temperature of the dust, if you look at the evolution with redshift, this doesn't seem to be as extreme as some of the models might predict. So the temperature is increasing slightly towards earlier times, but it's not as dramatic as you might expect. And that also means that the dust masses we're inferring might be a little bit higher than what you would get if the dust was actually a lot hotter. And all of this has really been quite challenging for models, because at such early times, we didn't really expect that dust grains would be formed so rapidly. And one thing to take into account, though, is that the ISM, so the interstellar medium in these very early galaxies, is actually a lot denser than what your typical local galaxy will have. So the ISM density is a factor of 40 or even more dense than locally, which might facilitate then an efficient growth and formation of dust grains. So as a reaction, really, we've seen a lot of developments in models which mostly look at supernova events, asymptotic giant branch stars, and also the direct growth of dust grains within the interstellar medium. And all of these could potentially explain some part of the dust that we're seeing this early on. But of course, the question is, which one is the dominant one, and can we understand which of these is contributing? So here's a plot from a paper we wrote this year, and this is showing you the dust mass as a function of stellar mass, and all of the colored points here are high redshift galaxies where we have quite precise measurements with ALMA in order to be able to measure this, both the temperature as well as the dust mass. And you can see here in the black dashed line that this is sort of the maximum yield of dust that you would expect from typical supernovae and AGB models. And what you can also appreciate is that some of these points lie quite significantly above that, and even above this red line, which is showing what you would expect the amount of metals to be at a given stellar mass. And so this is already showing that there is some discrepancy, it seems, with the amount of dust we're seeing given the amount of stellar mass we're seeing. But there's also a problem here, because this dust mass, apart from being quite uncertain, there's also a degeneracy, because we can't really tell just from the dust mass whether this has come from supernovae or AGB stars or both. And so we need a solution for this. And one, I think, promising way to go forward is also not just to look at the total amount of dust we see, but also try to really measure the properties. And for that, I just quickly want to take a small break and just look at some pretty images from very nearby. So this is within our galaxy. This is an HST image of the Carina Nebula. And so what you can see here is basically this dusty cloud here at the bottom, which is, you can just about make out, hopefully, some of the stars that are peeking through this shield of dust. And every star is sort of is extinct by the intervening dust by various amounts. And the way we quantify this normally is by the extinction at a given wavelength, and this is just basically how in magnitudes how much flux you lose because of the dust absorption. And then AV, which I've already mentioned a few times, is just the extinction in at visible wavelengths. But then what happens if we now take this image and take it to a view from JWST, and you can just take a look at this star, for example, and then I'm sure many of you have seen this image of the same region, where now you can see this star that was previously, quite faint, even seen with Hubble. But then if you switch to these slightly longer wavelengths, the optical depth actually drops, and this star, which was clearly extinct by dust, now becomes very bright. And also you can see here in the bottom, there's actually many, many more stars that we now can observe at these longer wavelengths. And what this all gives rise to is what we call an extinction / attenuation law. And so what this shows us is the amount of the extinction you have as a function of wavelength. And this is just a compilation from a recent review that shows that if you look at different sources, so you can look at different stars and try to model, try to infer what kind of star it is, and then basically just divide the observed light you see by what you know the intrinsic star should look like without any dust. And you get this variety of behavior in the extinction. So you see some curves are quite steep and they have a lot of absorption at short wavelengths. And again, there's quite a variety here, also in different by different methods and papers. But all of this is thought to be caused mostly by the underlying dust grain distribution, and also the geometry of the whole system, which causes then the radiative transfer to slightly change things around. But one feature that I hope you can appreciate in all these curves is there's actually this what we call bump in the extinction curve around about 2,200 angstrom, and in some curves you don't see any signature of this bump, but in others it's quite strong, and there's really localized absorption around this wavelength. And this has been known for quite a while. So there was a paper already in 1965, and then a paper by Bruce Drain in 1989 saying that, even after 20 odd years of trying to understand this feature, it's still not entirely known what is causing this absorption. But since then, we have established that this UV bump is likely caused by carbon dust grains. And specifically, one candidate that I already alluded to is polycyclic aromatic hydrocarbons, or PAHs. And this is a paper by Irene Chevet last year, where she shows for galaxies at redshift 2 or so, still in the early universe, but not quite as early as I've been talking about, if you divide these up into bins of stellar mass, then actually the most massive ones have the strongest bump signature. And also we can see in emission of these pH grains that they have the largest amount of pH molecules. And so this, paints a picture where these pH molecules are responsible for the absorption around about 2200 angstrom. And so the question then is, since this feature can be quite strong, can we actually measure this in the early universe to learn something about the composition of dust? And that could actually be, a test case for how much dust is being produced by AGB and supernovae. And surprisingly, the answer turns out to be yes. So within JADES, we have this, in particular, one galaxy, which, and I won't take too much time here to go into the details, but I hope you'll appreciate that this feature, the absorption, is quite clearly there in the spectrum. And this was just not possible before, I want to say, before JWST, because even with JWST, this took 30 hours of NIRSpec time. And if you look at a Hubble image of this galaxy, an image and not even a spectrum, you can just about barely see it, and even NIRCam struggles to really detect it properly. But this shows just how powerful NIRSpec is, and we can get the full spectrum and quite significantly detect this absorption feature. And this is quite surprising because this is the first time that we're seeing it at a redshift greater than 3-ish. And it's telling us that there must be these carbon grains causing the absorption already 800 million years after the Big Bang. And just one other example at a redshift of 7 again, where we again see this quite strong absorption feature at the wavelength of the UV bump. So to look at what this means, as a function of redshift here, I'm showing the strength of the absorption. So we have this bunch of data points at redshift of 2, where from the work that I showed before, but also from a few other works, which are all, if you look at this color bar, quite massive systems, so high stellar masses. And our data point now is all the way out here, so very high redshift, very early on, but a pretty strong feature nonetheless. And then the question is, how do we interpret this? So we don't see any significantly evolved stellar population, so no sign for star formation that took place, beyond redshift of 10, which is then putting forward the theory that perhaps there should be some faster enrichment channel. And there's various ideas. One could be Wolf-Rayet stars, or potentially, supernovae of very low, very metal poor stars that can act as a very fast formation channel of these carbon dust grains. And this also ties in with a few other observational hints. So for example, if we look at some of the most metal poor stars in the Milky Way, we can actually see that a lot of these are very enhanced in their carbon abundances. And so it might be telling us, for example, that the metal production by the very first star, so the population 3 stars, could preferentially produce a lot of carbon instead of oxygen, which then would get us, dust grains that are more likely carbon-based. And just in my last few minutes, I want to quickly highlight a paper that was only has only been out for a few days now, where we got some more data on quite a lot more spectroscopic data on one of the highest redshift galaxies that we have confirmed before within JADES. And surprisingly, this now yields this very strong carbon-3 emission line at a redshift of 12.5. So this is really, one of the most distant galaxies that we know. And in fact, that emission line is now the most distant signature of any metal that we know within the universe. And when you try to measure the abundance of different elements, this carbon is so bright, the carbon-3 line, that it shows again a very a higher ratio of carbon to oxygen even than our sun, and by quite a bit as well. And so again, this could be the chemical signature potentially of these population 3 supernovae, which may have very different metal yields than the following generations of stars, so population 2. And with that, I think I'm probably already over time a little bit. So just want to quickly conclude that galaxies in the first billion years are very different from those we see today. And we generally see they have a lot less metal and dust content. But at the same time, it seems like some of them are actually, surprisingly enriched with metals and dust. And I've shown you some examples of dust continuum emission and even this 2175 angstrom feature in very high redshift galaxies, which is pointing us to considerable amounts of dust already being present so early on. And now the question is basically how do we explain this all? And I think it might be pointing us to formation timescales that are slightly shorter than what we might have thought before, and perhaps also, which I haven't really had a chance to talk about, but having more efficient dust destruction at a later stage of galaxy evolution. So I'll stop there and yeah, happy to take any questions. Thank you.
Okay, thank you very much, Joris. If anyone has any questions, please raise your hand virtually. Let's see. Meanwhile, I'd like to ask you, because what you see from your results is that the conditions of the ASM change very much. Like you were saying that it was 40 times as dense.
Yeah.
Does this mean that some of the calibrations, the empirical calibrations we use to measure things at high redshift start to break down, or is it expected?
Yeah, no, definitely. And that's a very good point. So I didn't talk much about some of the other science you can do with all of these rest frame optical lines. But for example, one thing we're used to doing with local galaxies is with the ratios of different emission lines to see, for example, if we think a galaxy is dominated by star formation or an active galactic nucleus. And what we're seeing in those calibrations is that because of the very low metallicity and also the high density of the gas in these early galaxies, is that the calibrations we've calibrated for local galaxies start to break down at high redshift. So I think that's definitely something to take into account. And also,
do you have an idea of at what redshift it starts to really break down, or is it in progress yet still?
So I would say just because of historically we've been able to do this out to about a redshift of 3. So I would say they're fairly robust up to that point. But just, yeah, because we've only, had just over a year of JWST observations, I think we're only starting to learn now how that changes beyond that redshift.
Thank you. Maritza has a question.
Yes. So thanks very much for this talk. I really enjoy it. So I'm very puzzled and intrigued about this graph where you show the temperature of the dust with redshift. So why the models? Why do you think the models are overestimating so much the temperature of the dust, or why it is lower than people
Yeah,
thought?
that's a very good question. I think the very simple answer would be that dust is very hard to model. So it's very complex. I haven't maybe told you that even in the local universe, we struggle quite a bit to actually make accurate models of the precise, extinction behavior that we see. And I think a lot of this complexity comes from the fact that these dust grains, they can vary both in size and temperature, of course, but also in composition. So every single dust grain can be a slightly different size. It can be hotter, it can be colder, and in a galaxy, of course, you'll have a full distribution of all of those quantities. And if you put that all together, it becomes a very difficult problem. So simply said, the models basically why you expect that the dust generally heats up is that these galaxies at higher redshift, they're more compact and they're forming stars at a higher rate, and so that means you're heating up the dust more efficiently, basically. But how much more efficiently, that's just that really depends on a lot of factors. So it's difficult to predict. So actually, I think here maybe I wasn't completely fair. The green line is a model, so this is from a simulation, but then this blue line, for example, is just an empirical fit extrapolated to higher redshift, and then this red line again is an observed trend, but again making certain assumptions on the properties of dust. So I hope that answers your question. In general, things are quite complicated.
Thank you.
Okay. Any other questions?
Yes, I have a question.
Okay, go ahead.
Thank you for the talk. My name is Almudena Prieto. It was very nice. I have a doubt you want about this association between seeing the metals, carbon, and dust, because it might not be entirely related in a way that you see the carbon lines, but you see in the gas phase. No, they are not blocked in dust. There will be a block in that you won't see it. So you simply see, it's true, one has to explain the production of this metal, carbon.
Yeah.
But I do not know why it has to be directly associated with the presence of dust. We know that dust is made with carbon and other metals, but the fact that you are seeing, it means that you see just in the gas phase.
Yeah, no, I agree. It's one thing to produce, carbon atoms that are released into the interstellar medium, but then, of course, in order to explain the absorption, you need to then also explain that somehow they coagulated into dust grains. I think it's more of the reason I mentioned this case of tying it in with potential carbon enrichment in very early galaxies is that the usual expectation from dust production was that because in the local universe, at least, we explain most of the carbon dust as coming from these asymptotic giant branch stars, which then take hundreds of million years before they actually reach that phase and start producing that dust. So in the very high redshift regime, the main thinking was that we don't have that much, we don't have that AGB source of dust yet, and so then likely you'll have more sort of silicate, oxygen-rich dust. But instead, if you if you would preferentially produce a lot of carbon by these first stars to go off in supernova, then you might expect actually that could lead to also having dust that is rich in carbon. So I hope that answered your question somewhat.
Yeah. But if I can pose another question
Mhm.
regarding the explanation of the shape of the ALMA spectral distribution, you show a case where you fit it with a modified by black body, and you infer an amount of dust. Well, maybe other possibilities can explain that shape, or just simply always by default putting a black body spectrum. I know we all do that, but you were talking maybe we have agents as well at this high redshift, as one of the samples you showed, no, that it was showing very high insertion lines. So not necessarily you have a very small range, spectral range, could be due to other components, other mechanisms. I wonder whether has been looked at, or just simply by default you put a black body, which acknowledge we tend to do that, but might not be the unique solution.
As well, I think first of all, we're very limited by just the amount of data, because you know, if you look at the number of sources where we actually even have a few data points on the SED, then they're basically in this figure. So it's you know, you can count them on two hands. So that makes it difficult to say something about, you know, large samples of galaxies. I do think with respect to the AGN point of view, that in principle this at least the cold dust component shouldn't change much, where you would potentially see more of a changes in the mid-infrared, sort of the higher, the really quite hot dust. But I think the cold dust component, so this is really the sort of typically 20-30 Kelvin dust. Even if there is an AGN in some of these systems, that will just behave like a thermal emitter. And so I think we can be pretty agnostic as to fitting the far infrared part of the SED at least. It's another question when you try to, of course, tie in both the far infrared with what you see at UV and optical wavelengths. I think there, if you're trying to, what many people do, for example, is to put a balance between the energy at short and long wavelengths. And then if you're influenced by AGN activity, I think that might complicate things. But do you agree?
I was wondering whether this shape that you see could be fitted by something else. So this solution is really unique, and I think maybe you need more. There could be other things there. No, I'm not saying that you had to make the fitting more complex. I say that maybe other mechanisms can explain that.
Yeah, no, I
that's
think
the point.
Okay,
Not to make it complex, because of course it's very few points, but not only a thermal component might explain this.
Right.
So
Yeah.
the point I wanted to make.
Yeah, that's a good point. I agree. Yeah.
Thank you.
Okay, so there's not any further questions. I think this is a good point to end. Thank you once again, Joris, for that wonderful talk.
Yeah, thank you.
Well, that's it. Bye, everyone.
Bye. Thanks.
Thank you.
Thank you, Joris. Bye.